Good morning. Welcome to Krishna's class. Let us look at some results related to the measurability of given sets. Particularly, the measures that one measure from a space will induce in the other through a mapping. Okay, let me start with this. Let us look at the theorem. So the theorem says, first of all, let us see what exactly you have. You have a set X with a sigma algebra on it. So this is a measurable set. With a sigma algebra. Then you have a topological space Y with a topology tau Y. That means the elements of tau Y are called the open sets that you have. Now what you have is the following. F is a mapping of X into Y. Okay. Now here you have a collection of sets which forms a sigma algebra on it, and Y is with certain tau Y. Now we are not assuming it's just a map from F from here. So we are not assuming F is measurable and so on. There is no such assumption at this stage. Okay. Now what do? We take subcollection of sets or a subsets of Y with the property that it's pulled back. It's pulled back. Into X is an element of, now this is assumed to be an element of F. Okay. So our claim is the following. So let us look at this set. Omega is defined as a set of all E contained in Y such that now this is the crucial set that we consider. So what does this give? It identifies a collection of sets in Y. Okay. Now our claim is that then omega is a sigma algebra See, the significance of this result is that from a sigma algebra on X and functions defined from X into Y, where Y is a topological space, you can construct different sigma algebras on Y. Okay, once we prove this result. So that's a way of generating new sigma algebras. Now this sigma algebra is, see, omega is essentially dependent on two things. one, it is dependent on F and also F. Okay. So omega depends on both F and F. So when you vary F, you get different sigma algebras on both. Okay. Right? You fix your F. Otherwise, if you vary F, you will get different sigma algebras on Y. Okay. If you vary both, you get a whole collection of sigma algebras. So there is a nice way of constructing new sigma algebras. Now this is the significance of this. Okay, so this is what we want to prove. So our claim is that this is the claim that you have. So what do we have to prove? See, you observe that omega is a subcollection. Omega is a subcollection of elements in Y. Omega is a subcollection of elements in Y. And now we are saying that this is going to be a sigma algebra. So what all things you need? See, omega is a sigma algebra if the three things are if one, Y is an element of omega. 2, A belongs to omega implies A complement. Third, collection AN union AN is also in. That means countable union of sets in omega is in omega. So first of all, Y is in omega, A is in omega implies A complement is in omega. Countable collection of subsets of omega belongs to omega, then their union is also in. These are the three things that we have to prove. Okay, let's start proving one by one. Okay, let me remove. Okay, let me take out this. Then, now we know what exactly the conditions are. Write down the proof. So we have to prove these three things, namely that Y belongs to omega. If A belongs to omega, then A complement belongs to omega and AN belongs to omega for n equal to 1 to infinity. Sorry, this collection is a subcollection of omega. That means each AN is in omega and their union is in omega. So first. Now let us see, we observe that Y equal to observe that f inverse of y equal to x and which belongs to x. That's on the definition. Which implies, so that completes the proof, the first statement. The second statement is this. A belongs to, A is contained in omega, implies A complement A is an element of omega, implies A complement belongs to omega. Now you see that, let's work out f inverse of A complement. F inverse of A complement is essentially F inverse of minus A, because A is contained in Y. Okay. Now this is equal to x minus F inverse of, that's easy to prove. Okay. Now that's equal to F inverse of A complement. And F inverse of A is in omega, therefore its in x, then its complement is also, is in M, implies F inverse of A complement is also in A. So this belongs, right? So that is proved. What does it mean? This means that proves part 2. Now let us prove the part 3. Part 3, what we have to prove? This is what we want to prove. That means omega is closed under countable union. How do we prove that? Now let us write down the proof. Now An belongs to omega implies F inverse of An in F. Okay. Now F inverse of etc. This is equal to now each one of these is an element of M, okay, which belongs to why it belongs to M? Each of this belongs to M. Therefore, their countable union is in M because M is a sigma algebra. So that completes the proof of this part. Okay. So now we go one step further. We put a further restriction on F. Then what do you get? This is the next case. So we have proved that whatever be the function that you take from x to y, see that this omega is a sigma algebra on. Now we further assume, so the case 2. So let us take the case 2. Right. Assume that, we further assume that F is what do you mean by that? You see, F is a map from X to the topological space Y tau. So if so, this means the following: if V belongs to is an element of tau Y, then F inverse of V that's the meaning of F is measurable. Okay. This is the assumption. Now let us if V belongs to tau Y, then F inverse of V belongs to M. That is the meaning of saying that F is a measurable function. Then what do you get? What is the conclusion? Then what we have is that every Borel set in Y E contained in Y has the property that what does it mean? It means every Borel set E is contained in omega. That is in dy is the porosity. This is the conclusion. Porosity in y is what? You take elements of tau y and then form what is called a complementation as well as countable unions, and then you generate a set of this kind, and this is what is called the moral set. Okay, and this is contained in, or in other words, you take all the open sets, choose the smallest sigma algebra that contains that. So this is what you call the moral set. Okay, dy okay, so let us now okay, so let us prove this result. So we choose V belonging to tau y. When F measurable implies, what does it say? F inverse of V is in it. Now let us take a countable connection. Countable collection of open sets. Y. That means elements of tau y. We prove that their union is also in, okay, then you know that their union is in tau y. What we work on is their pullback. Now you know that for each Vn being open and F being measurable, so Vn omega, because F inverse of Vn belongs to F being, this is where we use measurability. Okay, now we will work out this. So we look at this one, F inverse of This is equal to Vn of F inverse of Vn. And F inverse of Vn is a element of M. M is a sigma algebra, and this belongs to M because therefore, now you see, this is an open set. But what we want to work on so one can observe that the oral collection generated by tau y say my star is a collection. And M is the one which is having the property that their pullback under F is in F. If E is a Borel set, Y that is Y star F inverse of E belongs to so this is what we want to do. And that is our statement that so this completes the proof of that. Okay. So that is the proof of. So what we have is what we observe is that My star, it is the Borel set generated by tau y in Y is a subcollection of omega, because this being we have proved that all the open sets, see, this is what we have. Tau I is contained in omega. Therefore, what we get, omega being a sigma algebra, you see that my star is contained in omega. That's how you get it. My star is the smallest sigma algebra that contains tau I. Okay. Therefore, once that is there, see, if E is a Borel set, E is in my star, then you have F inverse of E belongs to M because E is in omega. Omega consists of all those sets for which F inverse of E is in M. So that completes the proof. Now we take up the third statement. The third statement is significant because it is a special case and it talks about the condition for measurability of maps from the measurable space XM to R star. R star is nothing but the extended real line. So this is what is the statement? We have it. Yes. See? This is taken as Y in this case. Then we assume F inverse of alpha infinity this is a crucial. This is a condition for measurability of extended real valued functions on a measurable space. Okay. So right here, remark measurability of extended real value functions on so let us prove this. So, it's a remark. So what is that you have to prove? Okay. You want to prove that okay, I have not made this statement. This implies F is measured. So what do we have to? We have to show that if V is an open set, okay, this is what we want to prove. Okay, that would assure that F is a measurable function. So let us look at some of the properties of the open sets on the extended real line. V is open now V can be expressed as the countable union of where is an open interval so for all, so you can write V as the union of these open intervals. Okay, so it is sufficient to prove that. So you see that you can easily get F inverse of V F inverse of 10 equal to beta n and therefore, and you see that if you prove F inverse of alpha n beta n is in M, then it implies F inverse of B is in M. So therefore, if so the problem is now reduced to proving that the problem is now reduced to proving that F inverse of the interval alpha beta for every real assembly. So the problem is now reduced to proving that this belongs to So let us prove this now. What is given? What is given is this. That is F inverse of see, we do one thing. Observe that the interval alpha beta is then equal to the intersection of two intervals minus infinity beta alpha. So it is the intersection of these two. So it is sufficient to show that and F inverse of alpha beta is equal to F inverse of minus infinity beta and intersection F inverse of so this we already know. It belongs to M. For every this part belongs to M. So it remains to prove that this type of sets belongs to. That's it. So what we claim is this. F inverse of how do we prove this? Okay. This is the real line. So you are talking about this set. Talking about this set. Now this set can be written in the following. Note that is equal to the union of the collection minus infinity beta n infinity this interval where beta n is such that each beta n is less than beta and beta n tends to beta as n tends to. That means given beta you can find a sequence here. Beta n. Okay. So the problem is this. See, this has the property that F inverse of minus infinity beta is in M, provided this has the property that this is in or F inverse of this is in. So let us prove that. The next task is this. So we reduce this in various stages. One part is already in. How to prove this part? Simple. Now you observe that complement. That is true. Okay. Now you see that F inverse of which implies its complement. Okay. But what is that? That's equal to, but F inverse of this is equal to what? F inverse of complement. Okay. And therefore, you see that this is in M means, which implies F inverse of F inverse of what is the complement of this? The complement of this is this. And that's what we wanted to prove. This is true for every. Therefore, what do you get? Which in turn implies F inverse of Peetham. So that is the conclusion that we want. Therefore, what we have? So we have the following. This is in omega. So okay. So this is in omega. This set is in omega. The other one is also in omega. Therefore, you have the following. Yeah. Because we have got F inverse of alpha infinity is already in. Okay. So this mu alpha in. And this is nothing but uh, inverse of alpha. See, this is in M, this is also in M. That's what we have to do. And therefore, this is in M. And therefore, we conclude that F inverse of now we trace the path. So what we prove is that every open interval, the pullback of every open interval is in there. Okay. Therefore, the pullback of their arbitrary unions is in. Okay. Right. So for every open set, so from this we conclude so just one condition would enable you to prove that F is measurable. Or there are equivalent conditions like, these are all the equivalent conditions. That is F inverse of minus infinity down to M. This is one condition. F inverse of minus infinity. So all equivalent conditions. F inverse of 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 alpha Now these are all equivalent conditions. So what for? Now these are all equivalent conditions. One can try to work out a proof for each one of these. Okay, so that completes that. Now it remains to prove the following. Okay, what is the fourth statement? You have same y so this is measurable. This is topological. This is again topological. And you have f is a map from x to y, which we assume is measurable. It's a measurable. Then what is that you are assuming? These two are topological spaces. So you see that G from Y to Z is assumed to be a Borel map. Okay. Then what you conclude is that H is measurable. The composition H is measurable. Now you see that it is enough to prove that G is a continuous map. G is a continuous map, then G from Y to Z is F H given by G composition F, where F is measurable, G is continuous, then this is going to be measurable. So let us prove this. This is again simple to okay. So let us take V as an element of, that means V is open in that's the meaning. Now we want to prove that what is given, G is Borel, which implies G inverse of V is a Borel set. G inverse V is a Borel set. Why? I mean, associated with tau 1. Therefore, what do we have? This implies F inverse of G inverse of B. G inverse of B is Borel. F inverse of G inverse of B belongs to A. Okay? Because F is functional. H is equal to then H inverse of B equal to which belongs to, that means which implies now this is what we want to conclude. This completes the proof of this theorem. I think I'll stop here. And I had an earlier recording of this. I thought that I'll change it because to bring some clarity. Thank you very much.